Our next presenter is Phoebe Peng from the University of Sydney, and Phoebe will tell us about enhancing table tennis to make it more accessible for those with vision loss.
Hello everyone, I'm Phoebe Peng from the University of Sydney, and today I'm going to talk about an assistive technology for blind table tennis, which uses sensory augmentation between sight and sound. So firstly, for some motivation and background. Around the world, there are an estimated 285 million people who are visually impaired, of which 39 million are blind. In the field of sport, adaptations for the blind often sacrifice important aspects of the original game. In vision-impaired table tennis, known as swish, the 3D dimensionality is removed as the ball is rolled along the table under a barrier, as pictured here. We aim to design a system which would retain the original design of table tennis and help players identify the ball traveling in 3D space. The method to do so involves combining event cameras and spatial audio. Event cameras are image sensors and an example of neuromorphic engineering. Rather than working with frames like a traditional camera, each pixel asynchronously reports changes in light. Spatial audio manipulates signals from speakers to create a virtual sound source. We wanted to explore the possibility of using this novel technology with spatial audio. To begin designing the system, some data was collected from the event cameras. A motion capture system was used to track the ball for validation testing. Several games of regular table tennis was recorded and then used in development. The first phases of the development was ball tracking. Due to the asynchronous nature of the event cameras, they are ideal for real-time projectile tracking. Instead of needing to process an entire frame, only the relevant pixels are considered. However, to work with these cameras, established methods for traditional cameras do not apply, and hence more novel methods had to be used. The first step is calibration. The issue arises that traditional calibration involves capturing images of regular patterns. Event cameras cannot form a typical frame and only detect moving objects. The simplest way to get around this was to reconstruct images. We tried several simple ways, such as moving a printed checkerboard or using a flashing screen. These early methods did not provide a clear enough image. The solution was to map colors temporally rather than directly to the polarity of events. We captured a stream of a checkerboard that alternated between black and white squares. Using this reconstruction technique, we were able to calibrate our cameras. The next step is feature extraction, which means extracting which events represent the ball. Again, the usual techniques can't be used due to lack of a frame. Instead, the approach was taken to use dbScan algorithm to cluster events based on density. In this visualization, we see the green boxes indicating where clusters have been detected. A red circle indicates the cluster identified as the ball. The distinguishing of the relevant cluster is done through simple parameter weights that take into the ball's position, proximity, and last track location, as well as cluster size and density. A single camera cannot determine the depth of an object. Hence, two cameras were used, and triangulation of the 3D point from the 2D pixel coordinates were done using direct linear transformation. The next phase in the pipeline is to transform the 3D position to audio signal. The idea behind spatial audio localization is taking advantage of interaural time delay differences. We perceive a different delay of when signals reaches the left and right ear, which informs where sound source is located. The sound source can be simulated by having a listener positioned between speakers which play different signals. The method used to create this virtual sound is audio panning. The signals between the loudspeakers differ in amplitude to create the illusion of a sound source emitting from between loudspeakers. The setup we use involved two levels of speakers on each side of the table to give height and depth. With this initial prototype, we've identified what the next steps are for this project. After a year of development, we have a solid basis, but there's much room for further work. We hope to improve the spatial audio and look more deeply into the effectiveness of different signals and human perception of sound localization. The computation time of the camera tracking needs to be lowered. To be truly real-time, having a predictive model for the ball trajectory would be ideal. For purposes of usability, streamlining the setup process would make the system much more usable. We also hope to explore introducing haptic feedback through the pedals. This project is in early stages of development, and it will be exciting to see where it goes next. Thank you, and I'll now be taking questions.
From Carrie Seeger, what are the most robust signals in table tennis for noisy gyms?
Most robust signals, sorry, just to clarify, is that on the sound side or as in tracking the ball?
Um, Sounds. Thank you for clarifying,
Sound.
Carrie.
Yeah, so with the natural sounds that a table tennis produce, you get two main audio cues, which is from the pedal and the ball being hit together, and also collision with the table. And those are quite distinct, and even in a noisy gym, I guess they'd be uh, relatively easy to identify. With this system, the loudspeakers are quite, I guess, loud. So even in a noisy environment, um, theoretically it could work, but if the noise is too much in the environment, it may be difficult to perceive the sound from the loudspeakers. Um, Hope that answers the question. Yeah.
I have a question, just out of personal curiosity. Did you play a lot of table tennis before working on this project?
Um, Actually, I didn't play too much, just casually, I guess. Table tennis is pretty accessible, I guess. In public spaces, you find a lot of tables. During my internship, we had one in the office as well, so sort of just every now and then. But yeah, I didn't play too much. I wouldn't say I'm yeah that good.
All right, looks like we have another question. Avery Thompson asks, what kind of sounds are you using to track the ball? Have you studied different sounds affect the ability of players to track the ball's position?
So in our current system, we haven't gone to the stage of testing with live players, especially with blind participants. Um, but we do know that in general, continuous sounds is better for identifying localization of objects. At the moment, with this initial prototype, just due to time constraints, we only did use a single stopped sound that was played like multiple times. Um, but yeah, we definitely want to look into more on what different signals affect tracking of the ball, but haven't quite been able to do that yet.